Hi guys, in this video we're going to talk about the relationship between pressure and the number of particles in a gas. We got some Cornell paper we're going to use and we'll do a couple of examples on how to solve those problems. So let's get going here. Okay, so here's our Cornell paper. Our purpose, this goes with 3.4 pressure versus number of particles, and don't forget to put your name, class period, and date over here. And then I've got some stuff that I already typed up to save a little bit of time in the video. Pause if you need to. Okay, so our essential question is how are pressure and number of particles related, and how do I use the relationship to solve problems? Okay, so you just did a lab, and in this lab you put more particles in the same amount of space. So we had a syringe and we put a little bit more particles in, and then we squished it back into the same amount of space, and then we put some more particles in and squished it down so that it was always taking up the same space because we had to keep the volume constant. And hopefully the line that you saw looked something like this, perhaps a little straighter maybe. And that type of relationship is called linear, more specifically positive linear, and that means that they change the same way. So I wrote same right here because that's important. What that means is that when the number of particles goes up, so does the pressure. Now this has to do with the bouncing, and if you put more people in a room, there's going to be more bumping. That makes sense, right? And if you have less people in a room, you have less bumping, so less particles, less pressure. Okay, so let's talk about how you use this relationship to solve problems. And we've got an example problem right here. Our example one, 5 moles of a gas in a rigid container is at a pressure of 765 mmHg. If 5 more moles of gas is added, what will the pressure be? Okay, so let's see what we've got. 5 moles of a gas in a rigid container, pressure of 765 mmHg. 5 more, and this more here is going to be really important, moles, what will be the pressure? Okay, I'm going to zoom in some here. Okay, so I'm going to put pressure on one side and number on the other. And I've got 5 moles to begin with, and a pressure of 765 millimeters of mercury is that unit. Those units are going to stay the same. Moles always measures this. Now I have to do a little bit of thinking here. If I start with 5 moles and I add 5 more moles, how many moles will I have altogether? 10. So 10 more moles, or 10 moles is what I'll end up with. So this is my initial, this is my final, and down here I'm going to use thinking about the change to help me know what to do with my numbers. So you can see that my number of particles is going up. What will happen to my pressure? Well, they do the same thing, so I'm going to draw an arrow pointing up over here also. If my number that I get isn't bigger than 765, then I probably did some math wrong. All right, so let me switch colors here so we can see what we're doing. We'll go with blue. All right, so I got to think about the change here. 5 to 10, I doubled. That's times 2, right? I doubled the number of particles. So what's going to happen to my pressure? Well, it's going to double also. So 765 times 2, and I get 1530. Same unit, mmHg. So if I double one, I double the other. That's pretty easy to think about, right? If you're not sure what to do, you can always plug some numbers in your calculator and see what happens, but it's always a multiplier. Here we added, that was something separate just to be able to get the numbers in the chart, but we're always multiplying or dividing, okay? So 1530 mmHg is my final answer. All right, let's take a look at another example. Here it is. All right. It's a little laggy here. All right, example 2. A sample of gas at 14.2 psi has 12.7 moles of gas. How much gas must be present to have a pressure of 27.2 psi? All right, so pressure and number. 14.2 psi, that's a pressure. 14.2 pounds per square inch is what that stands for. And 12.7 moles, that's the number, so 12.7 moles will go over here. How much must be present? how much, that I'm looking for the moles again, the second number, to have a pressure of 27.2 psi. So the 27.2 psi goes here. Now if I look at this, 14.2 and 27.2, well, if I had double 14, I'd have 28. So I might have almost double the 12 also. So let's think about what happens here. My pressure goes up, my number has to go up. Okay, so to get from here to here, what I'm going to plug into my calculator is 27.2 divided by 14.2, because it's almost double, but it's not quite. So let's see just how much it is. 27.2 divided by 14.2, and I get 1.91. 1.91. So I must have multiplied by that 1.91 to get to the 27.2. So I'm going to do the same thing to my number times 1.91. They're always the same. Remember, it was a linear relationship, so I'm going to be doing the same thing. So I'm going to take that number in my calculator and I'm going to multiply by the 12.7, and I get almost double, 24.32, which actually that kind of looks like double. The 24 does at least, but the 32 is not quite as much. Okay, so my answer then, I forgot my unit, is 24.32 moles. The unit will always be the same as whatever the unit was to begin with. Excuse me, so make sure that you're paying attention to that one. One more example. Example 3. A rigid container with 6.2 moles of gas has a pressure of 1.25 atms. What will be the pressure if 2.1 moles of gas is released? Okay, so some important information, 6.2 moles, pressure of 1.25, 2.1 moles of gas, and then I'm going to circle this released here because that's going to tell us what to do with that 2.1. All right, so my number, whoops, I like to put my pressure on this side and number here. The number started out at 6.2 moles. We have a pressure of 1.25 atm, which means that my answer will have the pressure atm. And it says that I'm losing 2.1 moles of gas. 2.1 moles of gas is released. Am I going to write 2.1 for my final number? No, because it doesn't say I end up with 2.1 moles. It says I lose. So I'm going to do 6.2 minus 2.1. That's a minus sign. 6.2 minus 2.1, and I get 4.1. So 4.1 moles is what I'm going to put here. All right, so this time my number went down, which means I have fewer particles to bump into each other, so my pressure goes down. So now I want to think about what happened. Okay, to get from the 6.2 to the 4.1, I'm still going to divide. And I like to divide the bigger by the smaller, but I don't have to do that. So I got 1.51 here. I must have divided by that number because it got smaller, okay? If you're going to take the bigger divided by the littler, then you have to think about whether you're getting bigger or smaller as to whether or not you divide or multiply. But I got to do the same thing over here, so I'm going to divide by 1.51. All right, so 1.25 divided by 1.51. Do make sure that you get those numbers in the right order in the calculator because you might end up with something wrong. All right, so I got 0.83 atm. I rounded. It actually says 0.827, but that 7 tells me that I should round up. So my answer is 0.83 atm. 0.83 is less than the 1.25, so I did get an answer that is smaller, just like I was expecting. Okay, so mental note, when you're dealing with the number problems, you might have to add or subtract to figure out what goes in this box or this box because we're thinking about the change in the problem, but we've got to figure out the multiplier in order to be able to do our problems. All right, if you need to see more examples, make sure you ask your teacher, and thanks for watching.